Hello everyone, welcome to this video lecture. In this video lecture, I will be discussing about the third Maxwell's equation, which is also called the Faraday's law. The differential form of the third Maxwell's equation can be written as the curl of electric field is equals to minus del B del T, and the integral form of the third Maxwell's equation can be written as E dot d of L integrated over a closed loop is equals to minus d phi b by dt, where phi b is the flux of the magnetic field passing through a closed loop. So what this Faraday's law basically means is that if there is a time varying magnetic field in a region, then an electric field is formed around that region. So suppose this is a time varying magnetic field in a region. Now, because this magnetic field is varying in time, an electric field will be formed around that region, something like this. So an electric field will be formed around the region where the magnetic field is changing. Now if we keep a conducting loop around this region, then we will get a current that flows in the conductor, because we are putting a conductor in an electric field. So we will get a current that flows in the conductor. Now the direction of this current, or the direction of the electric field that is formed around this region, will be given by the Lenz's law, and it will depend on whether the magnetic field B is increasing or it is decreasing. Now I will be showing that the differential form of the third Maxwell's equation and the integral form of the third Maxwell's equation are equivalent. We can obtain one from the other. Now before trying to show the equivalence, we have to know about the Stokes theorem. What the Stokes theorem says is, if we take the curl of a vector quantity, say f, and integrate it over a surface, then this integration is same as the line integral of that vector quantity around the boundary of the surface. Now if we have to understand what this means physically, let's consider a hemispherical surface, something like this. And now if we calculate the curl of a vector on top of this hemispherical surface and we integrate it over that surface, then this integration is the same as the line integral of this vector quantity f around the edge of the surface. So if this is the edge of the surface, then it will be the same as taking the line integral of the vector quantity around the edge of the surface. So this is what the Stokes theorem means. Now if this, instead of a hemispherical surface, if we take a surface something like a balloon, suppose we take a surface something like this, we can also consider a surface like this. Now if we take the curl of a vector quantity and integrate this over this surface, the suppose the surface of a balloon, suppose this is a balloon, then this is the same as taking the line integral of this vector quantity f about this boundary here. So this is f dot d of l. Okay, so and so now if it is a closed surface, then the curl of the vector dot d of s will be 0, because the line integral, because this line will be 0. Okay, so now that we have discussed about the Stokes theorem, let's see how we can obtain the integral form of the third Maxwell's equation from its differential form. So let's write down the Stokes theorem, which is curl of any vector f over a surface S is equals to the line integral of that vector over the boundary of that surface. Now here in our case, we will replace the vector quantity f with the electric field E. Del cross E of S is equals to E dot d of L. We can choose any surface for this derivation. Now from the differential form, of the Faraday's law, what do we get? We get del cross E is equals to minus del V del T. This del cross E we will replace here. So let's give this equation number 3. So from equation 3, and let's give this an equation number 4. So from equation number 3 and equation number 4, we will get integral minus del V del T dot d of S is equals to E dot d of L. Now let's take the del del T outside of the integral, and then we will have integral B dot d of S is equals to integral E dot d of L. Now from definition, this is nothing but the flux of the magnetic field phi B. So from this we will obtain E dot d of L is equals to minus del del T of phi b, where phi b is the flux of the magnetic field lines passing through the closed loop, and E dot d of L is the integration or the line integral of the electric field around that closed loop. So we obtain the integral form. We obtain the integral form of the third Maxwell's equation. In the next video lecture, we will be discussing about the fourth Maxwell's equation, where we will see that a time varying electric field can produce a magnetic field. Here we have discussed how a time varying magnetic field produces an electric field, and the fourth Maxwell equation will deal with the case where a time varying electric field produces a magnetic field. Thank you.